Hello everybody and welcome to our first lesson in Unit 2 on absolute value and piecewise functions. Today's objectives are, given the equation and using a transformational approach, graph a function. Using a transformational approach, write the equation of a function given its graph or a description of the transformations, and identify function characteristics of an absolute value function. And those function characteristics are ones that we already know and talked about: vertex, domain and range, maximum, minimum, increasing, decreasing intervals, intercepts, and end behavior. So let's think about absolute value. What is absolute value? You know it's written with absolute value bars, absolute value of x. The absolute value of x is the distance x is away from 0. And since it is a distance, that means that it cannot be a negative number. No matter to which direction the distance goes, it's just the absolute value of the number of units that lies between that x and 0. And let's look at our first function. F of x is equal to the absolute value of x. This is what we call the parent function of all absolute value functions. Let's go ahead and graph that function. And to graph any function really that you're not entirely sure what it's going to look like, the best and easiest way is to just create a table of values. I'm going to create a table of values using the values -2, -1, 0, 1, and 2 for x. And then f of x, the function of x, which is to say the same as the y, is +2, 1, 0, 1, and again 2. Let's go ahead and put the coordinate plane here. This is our y-axis and our x-axis. And I'm going to go ahead and plot the points that we have just jointly come up with. -2 and 2, -1 and 1, 0, 0, 1, 1, and 2, 2. If we connect these points, we get something that's V-shaped, shaped like a V, and this is what the graph of our parent absolute value function looks like. Let's analyze the characteristics of this absolute value function, and you have room in the left margin of your note page to note down these things and fill them out. First of all, I want you to notice that the graph makes a very sharp turn at the origin, and this point we call the vertex. You know vertex from quadratic functions from algebra 1, and it also looks kind of similar. So the vertex of our absolute value function is 0 and 0. If we look at our domain, we go from -infinity to +infinity as indicated by our arrows. So I'm going to use set notation to write down the domain. Open braces x such that x is an element of the real numbers. Let's look at our range. The range doesn't go or doesn't come all the way from -infinity. It actually starts here, and it does go up to +infinity as indicated by our arrows. In other words, for the range, and this time I'm going to use interval notation, we are going to say open brackets 0 comma, positive infinity, close parentheses. Remember, the brackets indicate that 0 is part of the range, while the parentheses indicate that that element isn't. That can be true for a number, but definitely if a range or a domain go all the way to positive or negative infinity, we always have to use parentheses, never brackets. Let's look if we have any minima or maxima. I don't see a maximum. I do see a minimum, however, and the minimum is actually at the same spot where we had our vertex. So the coordinates of a minimum are also 0, 0. Let's talk about increasing and decreasing intervals. I see an increasing interval, which is essentially this part of the curve. And that increasing interval goes from 0 to positive infinity. And I also see a decreasing interval, which comes from negative infinity and stops at 0. Let's talk about intercepts now. Since the curve goes through the origin, you remember that from our previous unit, both our x and y intercepts actually have the coordinates 0 and 0. Let's move to our next example. And what I'm going to do is, in order to get an idea of what this curve is actually going to look like, I'm going to use the calculator and see what the calculator will give me for a graph. And obviously you can do the same at home or in class. I'm going to put in the equation. As you know, y is equal to, and then we start with the absolute value, math, go to the right, number 1, x, move out of our absolute bars, plus 1. And what I'm also going to do is I'm going to graph next to it our parent function and see how they're actually different. So again, math to the right, 1 for absolute, put in x, and that's that. Remember, our blue curve is going to be the new function, and red is the parent function. And if we look at that, we see that the blue curve got moved up one step. Other than that, it looks exactly like the parent function. Let's then go ahead and graph the function ourselves. First, I'm going to put in our coordinate plane, vertical y-axis, horizontal x-axis. And the points I'm going to use are 0, 1, 1, 2, 2, 3, negative 1, 2, and negative 2, 3. Connecting the points, this is what the function looks like. And we can now go ahead again and find the vertex. The vertex actually moved up 1 and is now at 0, 1. The minimum is that same point, 0, 1. And if we want to talk about intercepts, we see that now this curve no longer has an x-intercept. It does, however, have a y-intercept, and the y-intercept is also at that same point, 0 and 1. Let's move on to our next example. And I'm going to use the help of our calculator again. I'm going to change the first function to put in the new function we have up here, but I'm going to keep our parent function just as a comparison. Math to the right, 1 for absolute value x, and now inside the absolute value bars, minus 3. This is our new function. Let's look at what it looks like. As we can see, the blue curve has now moved 3 units to the right. Other than that, it seems to be looking exactly the same as our parent function. Let's go ahead and graph it. This is what it looks like, and I do want you to remember and actually write down here when we found negative 3 inside of our absolute value bars, the negative sign moved the graph to the right. We could, of course, now go through all the other characteristics as well, but I'd rather focus really on the changes, the transformations that we see. So let's move on to our next example. Get a calculator and change our first function into absolute bars x plus 2, and let's look what our blue function does now. The blue graph is now moved 2 steps to the left from our red graph of the parent absolute value function. 2 steps to the left. This is where our vertex lies, and we go up using the same numbers that we have been using before. There goes our graph. And now I do want you to note that when we had plus a number, the plus moves the graph to the left. And on to the next example. F of x is equal to 2 times the absolute value of x. 2 times the absolute value of x. Make sure that you keep the 2 outside of the absolute bars. Let's look at our blue graph now. Comparing it to the graph of our parent function, it has a vertex in the same place, goes down to the origin the exact same way, but it seems to be narrower, right? It goes up both to the left and to the right, far steeper than the red graph does. So we have a vertex in the same place, but instead of going 1 up, 1 to the right, we go 2 up, 1 to the right, 2 up, 1 to the right again, and 2 up, 1 to the left, 2 up, 1 to the left, to get a graph which is steeper. And if you remember what steepness really means, it's related to slope. So this 2 that's multiplied by our absolute value of x acts like a slope. We will also talk about it and call it dilation. And you do remember what dilation means from geometry, and we use it in a very similar sense in the transformations of functions right here. Let's look at our next example. Y is equal to negative 2/3 absolute value of x. So now if we have a negative here, I'm going to have you use parentheses and to make sure that we don't make any mistakes here. Negative 2/3 is what we're looking for, right? And here goes our graph. Look, it is two things. It's actually flipped downwards. The blue graph is flipped downwards, and that's what the negative did for us. And if you compare them also in terms of their width, you can tell that the blue graph is wider than the original graph was. Then let's go ahead and graph the graph of this function. Vertex is at the origin 0, 0, and now our negative 2/3 acts just as we said before, just like a slope. So we go down 2, 3 to the right, and on the other side we go down 2 and 3 to the left as well, which gives us our curve that we've also seen on the calculator, which is flipped downwards and is also wider than the graph of our parent absolute value function. All right, make sure you have all your graphs in your notes and then move on to the second part of the lesson.